Aromatic versus anti-aromatic versus non-aromatic. We're going to talk about in this lesson. So we're going to introduce the criteria for aromatic compounds, and we're going to see what makes benzene so special. And then we're going to apply that to a bunch of other related compounds, and we're going to have to fit them into one of these three categories. Are these compounds aromatic, anti-aromatic, or non-aromatic? We'll talk about like when is a lone pair going to count as part of the aromatic pi system, and when will it not, and how do I tell the difference, and things of this sort. By the end of this lesson, after we've worked about a dozen examples, you will have no problem identifying any of these three types of compounds. All right, so let's take a look at benzene here real quick and figure out what in the world makes benzene so special. So it turns out that the aromatic system of electrons here, so we've actually got delocalization. You could draw a couple of different resonance structures here. So you could draw the one we've got here, or you could draw this one here. And so what you've got is delocalization of pi electrons all the way around the ring. So there are no single bonds and there are no double bonds in benzene, in the ring itself. So what you've actually got are 1.5 bonds all the way around. And so you'll often see people kind of reflect this, because what you've really got is partial bonds all the way around. And so commonly you'll see people just draw benzene and they'll just put a circle in it. So, and for me, it just kind of looks like a birdhouse or something like that, but that's a common way of representing benzene as well. So, but typically you'll have drawn what are called these Huckel structures. So one of these two is typically how you represent it, but just keep in mind, regardless of if we draw a structure like this, you should realize there are no single bonds, there are no double bonds in benzene, they are all 1.5 bonds. And if we actually measure their bond length, we'll find out that they are shorter than a typical single bond, but longer than a typical bond, double bond, and they are all exactly the same length. If we actually had single and double bonds, we'd have, 3 long single bonds and 3 shorter double bonds, which is not the case at all. All right, so what is it that makes benzene so special? Because this system is conjugated and there is resonance, but it is actually much more stable and much lower energy than we would actually even predict. And so it created this whole new class of compounds we call aromatic compounds, which leaves you the lovely task of, well, how to identify aromatic compounds? Well, there's a few different properties of aromatic compounds, and we're going to use those criteria, we'll call them, to identify them. We'll see how benzene fits with each of these. So the first criteria is that it's got to be cyclic and conjugated. So you got to have a conjugated ring all the way around. So that way you get delocalization of pi electrons all the way around the ring. So if you look, you've got this parallel system of p orbitals all the way around the ring with delocalization all the way around. So every atom in that ring has to have a p orbital as part of this conjugated system. And they've all got to be able to be parallel, which will put some other constraints on us here. So that's criteria number 1. It's got to be cyclic and it's got to be conjugated. So but criteria number 2 is that every atom in the ring has to have a p orbital, a parallel p orbital as part of this system. Well, an easier way to actually kind of identify that is that you can't have any sp3 hybridized atoms in the ring. Because if you have an sp3 hybrid, that means that all 3 of your p orbitals have been used to make the sp3 hybrids. And if all your p orbitals are used to make hybrids, it means that particular atom won't have a p, just a plain old unhybridized p orbital left to be part of the pi system. So, typically on your study guide, it's phrased that every atom must have a parallel p orbital as part of the conjugated pi system. But my easier way of recognizing that this is satisfied is that there are no sp3 atoms in the ring itself. Okay. So that's your second criteria. So if we look at your third criteria, is that your ring has to be planar. And the idea is that you need a parallel system of p orbitals, and they're only going to all be parallel to each other if it is a flat structure. So it's got to be able to be planar. And this is not the easiest thing in the world to tell, so because some structures are planar and some are not. But we can make a couple of generalizations. If you have a ring that is 7 atoms or smaller, it will be able to be planar. So 7-membered ring, 6-membered ring, 5-membered ring. So notice benzene, 6 members. It can totally be planar. So that we can say with certainty. The unfortunate thing, though, is that if you have a ring that's 8 atoms or larger, some will be planar and some will be not. And so be careful with this, because I make the rule that if it's 7 atoms or smaller, it can be planar. A lot of students see that rule and they're like, okay, so if it's 8 or bigger, then it can't be planar. No, I didn't say that. If it's 8 or bigger, some are going to be planar and some are not. So, and we'll kind of look at some key examples that you're supposed to recognize in that regard. So that's going to be a little bit tricky. So, but oftentimes, because this can get a little bit tricky on identifying when some of these larger compounds are planar or not, sometimes you'll get a question phrased like, which of the following, assuming it can adopt a planar conformation, is aromatic, or something like that. And so they'll kind of throw this criteria out by saying, assuming it can be planar, so that way you don't have to worry about it. So, but that's not always the case. And so we'll see a concrete example of some of the larger rings of what you should assume are not planar, and one that you definitely should assume is planar, as we'll see here in a little bit. All right, so once you've gotten through all three of these lovely criteria, it turns out the number of pi electrons in your conjugated system totally matters. And this is going to be a little bit strange. So at first, but we're going to have what's called a 4n plus 2 pi electrons. So when you've got 4n plus 2 pi electrons in your system, and you've satisfied the first three criteria, that's going to result in your compound being aromatic. So it turns out not every set of number, every possible number of pi electrons works. So typically they're going to come in pairs, and so you could have 2 or 4 or 6 or 8 or some even numbers, typically the way it works. Well, it turns out if it's a 4n plus 2 number, we saw this in the last chapter on conjugation, this ultimately means an odd number of pairs. So notice one pair is 2 electrons, and that would be a 4n plus 2 number. So n here represents any integer, so starting with 0, so 4 times 0 is 0 plus 2 is 2. And so 2 would be an example of this infinite set of numbers described by 4n plus 2. That's a mathematical term, again, like we saw in the last chapter. So, but if you plug in 1, 4 times 1 is 4, plus 2 is 6, and 6 is an aromatic number, a 4n plus 2 number. It's also 3 pairs, an odd number of pairs. So you could have 1 pair, 2 electrons, 3 pairs, 6 electrons, 5 pairs, 10 electrons. Those are all aromatic numbers. They're all 4n plus 2 numbers. And again, this goes all the way to infinity, but obviously we're not going to have molecules with an infinitely large set of atoms and all that stuff. So, usually you'll deal with like 2, 6, and 10 as being the most common. But another way to look at this is you could start with 2 electrons and then just keep adding multiples of 4. 2 plus 4 is 6, plus another 4 is 10, plus another 4 is 14, plus another 4 is 18, and you're never going to get anything bigger than that in all likelihood. So that's usually sufficient enough. We'll see one large example here along the way. Cool. So again, you've first got to satisfy these first 3 criteria, but if you satisfy the first 3, and then you have an aromatic number of electrons, an odd number of pairs, or a 4n plus 2 number, so that is what ultimately is going to lead you to make the determination that this compound is aromatic. So if we take a look at benzene now, benzene is cyclic and conjugated. Fantastic. Cyclic, and then notice alternating single, double, single, double, single, double, which again is just resonance, but there's really delocalization going on. But again, in all our aromatic compounds, it's going to be delocalization. But in any individual resonance structure, you want to verify this kind of conjugation with alternating single and double bonds. Be the easiest way. We'll get a little more complicated examples in a little bit. So benzene, cyclic and conjugated, check. So no sp3s? Nope. Every single atom in the benzene ring is sp2 hybridized, which means they're all going to have an additional p orbital that's unhybridized available for delocalization, available for this aromaticity. All right, planar. Yep, 6-membered ring, and again, 7-membered ring or lower, it will definitely be able to be planar. 8 or higher, maybe it is and maybe it isn't. We'll kind of go through a couple concrete examples you're supposed to know. All right, finally then, we're going to go through the number of pi electrons, and in this case it's 2, 4, 6 pi electrons. That is indeed an aromatic number, and benzene is indeed aromatic according to the criteria we've just talked about. And so now you'll need to be able to apply this criteria to a variety of other compounds to figure out if those compounds are aromatic as well. Now, one thing to note, we've got a couple of other terms here. So one of them is anti-aromatic. So, and it turns out just like aromatic compounds are really, really stable, there's something called anti-aromatic, which are really, really unstable. So aromaticity lowers the energy significantly. Anti-aromaticity is going to raise the energy significantly. And so it turns out if you satisfy the first 3 rules, so then you're well on your way to being either aromatic or anti-aromatic. So, but you got to satisfy those first three rules first. So, however, if instead of having a 4n plus 2 pi electrons, so if instead you have a multiple of 4, so 4n pi electrons, then that's going to actually result in you being fairly unstable and being an anti-aromatic compound instead. So again, you still got to be cyclic and conjugated. You can't have any sp3 hybridized atoms in the ring. It has to be planar. But if the number of pi electrons is a multiple of 4, like 4, 8, 12, well, then it's going to be actually really unstable and be an anti-aromatic compound instead. And we'll see a few examples of this as well. So finally, your other term you got to be familiar with is non-aromatic. So, and I can't, non-arotic, that sounds terrible. It's definitely not the thing. So let's spell this correctly, non-aromatic. All right, so non-aromatic just means you failed one of these first three rules. Either you're not a completely conjugated ring, either you're not cyclic, you have an sp3 hybridized atom somewhere in the ring, which would again lead you to not being completely conjugated, or you're just not planar. You can't adopt a planar conformation of your ring. So any of these things are not true. You're not aromatic, you're not anti-aromatic either though, you're just non-aromatic. And so again, aromatic things are really stable in low energy, anti-aromatic are really unstable in high energy, non-aromatic are going to be somewhere in the middle. Kind of like non-bonding, not quite the same, but somewhere in the middle like that. Okay, so now we're going to put a few compounds up here, and like I said, we're going to take a look at more than a dozen examples and identify them using these criteria. All right, so the first four examples we're going to look at are these, and once again, we're just going to quickly use our criteria to figure out if they're aromatic, anti-aromatic, or non-aromatic. So our first example here is 1,3,5-hexatriene, something we studied in the last chapter, and it's definitely a conjugated pi system, but it is not cyclic. And once again, if you fail any of the first three rules here, i.e. by not being cyclic, then you're just plain non-aromatic here. All right, in the next example, so you'll notice this lovely carbon on top. So is unique. So these are all involved in making a double bond or sp2 hybridized, but that one right there is sp3 hybridized. And once again, you're not allowed to have any sp3 hybridized atoms in the ring, because if you do, you end up not having a completely conjugated system, and not every atom in the ring will have a p orbital. So these four are part of a conjugated system, but you don't have an entire ring of conjugation. So this sp3 hybridized atom does not have a p orbital to make part of an entire ring of delocalized pi electrons. So as a result, again, we fail rule number 2, and we are non-aromatic. All right, next one here, this is cyclic. It is a completely conjugated system, check. So rules number 1 and 2, I should say just 1, but 2, yep, all the atoms are sp2 hybridized. There's none that's sp3 hybridized. Okay, check. Planar, yep, 4-membered ring. Again, 7 or lower can definitely be planar. 8 or more, we'll see some are, some aren't. So definitely planar, but it actually has 4 pi electrons, which is a multiple of 4, or an even number of pairs, 2 pairs. So, and that is an anti-aromatic number, not an aromatic number. And so we passed all the first 3 rules, but we didn't have the right number of electrons. So this is anti-aromatic rather than aromatic. So super high energy structure, and we'll see in the last lesson in this chapter why it's so high in energy. So it doesn't seem right, like you're like, it's still conjugated, Chad. Yep, we'll get there. Next lesson. So, or last lesson, I should say. All right, then finally back to benzene again, and we'll just demonstrate once again that it is cyclic and completely conjugated. Every atom in the ring is sp2, so there's no sp3s. It is planar, being a 6-membered ring. Again, 7 or less, it will definitely be able to be planar. 8 or more, sometimes they are, sometimes they aren't. And then finally, this has got 3 pairs, i.e. 6 pi electrons, which is one of these 4n plus 2. 4 times 1 plus 2 is 6. And this, again, is aromatic. Cool. So that's our first 4, and now we're going to deal with lone pairs, and this is going to get a little bit more challenging. All right, so the next example here, this is pyridine, and it's a very well-known aromatic compound, it turns out. We'll find that out in a second. It's actually a pretty decent moderate base that's used for as part of a catalyst for a lot of different reactions. And But pyridine here, it turns out, is totally aromatic, but we'll follow the criteria to figure that out. So cyclic and conjugated, definitely cyclic, and then completely conjugated all the way around. So sp3 atoms in the ring, nope, there are no sp3 hybridized atoms. Every single one of these ends up being sp2 hybridized. So planar, yep, 6-membered ring, so it's going to be planar. So, and here's the tricky part, 4n plus 2 pi electrons. So, and it turns out it has 2, 4, 6 pi electrons. So we're going to find out what's tricky is it doesn't seem tricky now. It'll seem tricky in a little bit, and students kind of struggle, like, when does a lone pair count as part of the pi system? And we'll find out that sometimes a lone pair does and sometimes it doesn't, and you've got to be able to identify when they do and when they don't. So, but it turns out that this nitrogen is sp2 hybridized, and being sp2 hybridized, it's going to have 3 sp2 hybrid orbitals and then an unhybridized p orbital. Now, the pi electrons have to be in that unhybridized p orbital, but that means it's going to have these 3 sp2 hybrids, one for the sigma bond in this direction, one for the sigma bond in this direction, and the third sp2 hybrid is going to be where that lone pair resides. And so it's in an sp2 hybrid orbital, meaning it's not in a p orbital and part of the pi system. And so because it's not part of the pi system, we're not going to count it when we're trying to verify how many pi electrons there are. And so that's why we just counted 2, 4, 6, and the lone pair didn't count. Now, suffice it to say is this: when I look at this nitrogen, I can see his pi electrons right there in the double bond in this particular resonance structure. There's his pi electrons, and they're in the parallel system of p orbitals. Well, there's only one p orbital that can be part of that parallel system. Even if we tried to put this lone pair in a different p orbital, it wouldn't be parallel to the p orbitals in all the others. It would have to be in a perpendicular plane, like px versus py. And so you can only ever have one pair of electrons at any given atom involved in the pi system. And in this case, it's going to be those pi bonding electrons, not the lone pair. And what you ultimately end up with is making a rule like this. If the atom you're looking at is making a double bond, if it already has a pi bond showing in your resonance structure, then any lone pairs it has don't count as part of the pi system. They're just going to end up being in a hybrid orbital instead. All right. So we'll see how that contrasts to this next example here. So this next example, we'll add some pi electrons in there to make this interesting. So in this case, it looks like if you take a look at this nitrogen, in fact, let's take those back off for a second. If we look at this nitrogen here, before we put those pi electrons back on, I'd look at this nitrogen, I'd be like, he's sp3 hybridized, and I'd be right. And if you thought the same thing, then you'd be right. So because he is sp3 hybridized, except he might not be anymore if I do that. In fact, he's not. So when you guys learned this, back when we studied resonance back in chapter 2, and we learned that resonance can affect hybridization, I just want to take a look back at this guy down here for a second. He's definitely not aromatic, but for this guy right here, that nitrogen also is sp3 hybridized. In fact, why don't we draw those hydrogens out so we can definitely see that that's the case. But he's got 4 electron domains, 3 bonding domains, and then the non-bonding domains, and he's sp3 hybridized. If I put a pi bond right here, he's still, that nitrogen is still sp3 hybridized. Nothing has changed yet. However, if instead I put that pi bond right here, that nitrogen is no longer sp3 hybridized. It is now going to experience delocalization. It is exactly 1 bond away from pi electrons. Notice if that were on a carbon, we'd call it an allylic carbon. Because it's exactly 1 bond away from where there's pi electrons, there's going to be resonance. We could take and put these here. So forming a pi bond there, which pushes the pi bond to form a lone pair there. So lone pair becomes a pi bond becomes a lone pair. You might remember that pattern back from chapter 2. So, and we could draw another resonance structure here. In fact, we'll do it this direction where I've got a little more room. And so now when you look at this resonance structure, you'd look and say, oh, look at nitrogen there. He kind of looks like he's sp2, actually. Only got 3 electron domains. He's sp2. So this resonance structure looks like it's sp2. This resonance structure looks like it's sp3. But again, these resonance structures don't really exist. What really exists is the resonance hybrid that is the average of these two structures. But the key is this. sp3 atoms aren't participating in resonance. So you got to ask, is he sp2 or is he sp3? Well, is he participating in resonance? Yes. Well, then he's not sp3. He can't be. If you're sp3, you don't have a p orbital. That's what you need to have as part of a pi system. So he can't be sp3. And so when there's delocalization like this, when there's resonance, that nitrogen's actually sp2 hybridized. Even if you look at this resonance structure, again, that structure doesn't exist. What exists is the average of these two, and there's going to be partial pi bond character, some delocalization, and he can't be sp3. He's going to have to be sp2. And the same thing would be true right here of this nitrogen. This nitrogen right here is now sp2 hybridized, not sp3 hybridized. So the lone pair of electrons there is exactly one bond away from pi electrons. There's going to be delocalization. There's going to be resonance. Now, however, if I do this, things just get a little more interesting. So now I have a chance. Notice before this, let's take that one back off one more time. Before this ring would have two sp3 hybridized atoms in it. It wouldn't be completely conjugated. Only this side of the ring would be conjugated. And so because it's not completely conjugated and there's sp3 atoms, hybridized atoms in the ring, it is non-aromatic. So, but the moment I add this other pi bond into the mix, things get interesting. It is now still cyclic. It is completely conjugated now. So again, the atom with the lone pair here is one bond away from pi electrons on both sides. It's a completely conjugated ring. So there's no sp3 hybridized atoms in the ring because the nitrogen there is not sp3 hybridized. As we just learned, he's sp2 hybridized. Okay, so planar, yep, 5-membered ring can definitely be planar. So, and then how do we count the number of pi electrons? Well, in this case, this lone pair could be part of the delocalized system, could participate in resonance, if you will. So if we look down here, we saw that there definitely was resonance, and it was part of the, the lone pair is part of the pi system, the conjugated system. So, but with a ring, it gets a little bit complicated. So it has a choice in a ring. It can be part of the pi system or not, depending on if it makes it more stable. If it makes it more stable and it becomes aromatic, then it's definitely going to participate in resonance, be part of the pi system, be part of a delocalized system. But if it makes it less stable, if it actually turns it into an anti-aromatic compound, well, then it says, no, I'm not going to do that. So we got something at issue here of when you identify a lone pair as counting versus not counting as pi electrons. If it makes it aromatic, they'll count. If it makes it anti-aromatic, then it turns out it actually would be sp3 hybridized. And so in a linear structure, if you've got a lone pair on an atom, one bond away from pi electrons, that atom is not sp3. In a ring, it still might be, as we'll see. All right, so in this case here, if we look at then a criteria here, if you're on an atom with a lone pair, if that atom is not and have any double bonds in the resonance structure that you're looking at, but if it's exactly one bond away from double bonds from pi electrons, then it has a chance of actually not being sp3. So in this case, this nitrogen up here already has a double bond. That's where its pi electrons are, which means the lone pair is not part of the pi system. So, but here it's got a lone pair. That lone pair could be part of the pi system. Now, if you have multiple lone pairs, and nitrogen doesn't here, but if you have multiple lone pairs, only one of them has a chance of being in one of these parallel p orbitals. And so even if we had like an oxygen here that had two lone pairs, you only ever have a chance of one of those lone pairs being part of the parallel system of p orbitals and being part of the pi system. So that's the next thing. So if we look at this thing, so cyclic and conjugated, we said check. So no sp3s? Probably so. So planar, yep, it can definitely be planar, being 7 atoms or smaller in the ring. And then 4n plus 2 pi electrons. Well, if we count the lone pair, that would be 2, 4, 6. That's an aromatic number. That's an odd number of pairs, 3 pairs. That's a 4n plus 2 number. And indeed, this is an aromatic compound. Cool. Now, some of the things I said, just said in regard to the, when the lone pair counts and when it doesn't and stuff, probably didn't make a lot of sense. But it'll make way more sense when we see the counterexample with the one right below it here. So with this one right below it here, so once again, you've got sp2 hybridized atom here and here for sure. And the question is, what's the hybridization of the nitrogen? Well, if I cover up the bottom of this molecule, you look at that and be like, well, that nitrogen's got 3 bonding domains, 1 non-bonding domains, that's 4 electron domains. He should be sp3. And then I pull that away and you're like, oh, I didn't see that he was 1 bond away from pi electrons because you had it covered up, Chad. So maybe he's not sp3. If this wasn't a ring, we would just say he's sp2. But because he's in a ring, maybe he is and maybe he isn't. Let's see how this plays out in this case. So cyclic and conjugated, check. No sp3 atoms in the ring? Maybe. Planar, 3 atoms in the ring, definitely a smaller ring than 7, so definitely can be planar. And now we got to figure out how to count pi electrons. And so the question is this nitrogen sp2 or sp3? That is the question before us. So, well, it turns out whichever one leads to him being more stable, that's what he's going to be. So like in this case too, it turns out he had the same option. He could be sp2 or he could be sp3. Well, it turns out if he decides to be sp2, like he is, then he's aromatic, just like we determined. But if he decided to be sp3, well, had he been sp3, well, then we would have had an sp3 hybridized atom in the ring, and he would have been violating one of the first three rules, and he would have been non-aromatic instead. And so we asked our question, is it more stable to be aromatic or non-aromatic? Well, it's more stable to be aromatic, and that's ultimately what he is. Well, in this case now, we're satisfying potentially the first three rules, but when we go to count pi electrons, if he's sp2, then that lone pair will be in the p orbital in part of the pi system. Again, the nitrogen here doesn't have a double bond in this structure, so the lone pair would have to be its pi electrons, and it would be 2, 4. But 4 is an anti-aromatic number. And so in this case, if that nitrogen's sp2 hybridized, he'd have 4 pi electrons in the ring, and he would be anti-aromatic. And that's not good. That's super high energy, unstable. So he's like, well, what if I just decide to be sp3? So if he decides to be sp3, well, then we'd have an sp3 hybridized atom in the ring, and he would end up being non-aromatic. And so in this case, you got to ask yourself the question, is it more stable to be anti-aromatic or non-aromatic? Well, actually, now it's lower energy and more stable to be non-aromatic. And so it turns out that this nitrogen here actually is sp3 hybridized. And again, this is tricky. So once again, when your nitrogen in this case is one bond away from pi electrons, if it's not in a ring, then for sure it's involved in resonance and it's going to be sp2 hybridized, not sp3. But if it's in a ring, it depends. If being sp2 makes it aromatic, it's going to be sp2. If being sp2 makes it anti-aromatic, then he's not going to be sp2. He's like, I'll just be sp3 and be non-aromatic. And again, that's what we should determine for this structure right here. This guy is indeed non-aromatic. That's the deal. Cool. Hopefully we'll bear this out in a little bit. So one real quick recap. If the atom with the lone pair has a double bond in your resonance structure, the lone pair is not part of the pi system. It's just going to be in a hybrid orbital, like an sp2 like this. You're never going to count it. But if the atom does not have any double bonds involved in the structure, no pi bonds, then its lone pair has to be its pi bond or its pi electrons if it's going to have some. So in this case, it made it aromatic, and that was totally going to be the case, and that nitrogen's sp2. But in this case, it would make it anti-aromatic, so it says, I don't want to do that, just leave it sp3, and I'll be non-aromatic instead. Let's look at some more examples. All right, so the next three examples here, and look at the top one here. So cyclic and conjugated, check. So sp3 atoms in the ring. Well, let's see. So the only atom that looks sp3 is this oxygen, but he does have lone pairs, and he is one bond away from pi electrons on both sides, so he might not be sp3. Again, if he was in not part of a ring, we definitely know he wasn't sp3, he'd be sp2. But being part of a ring, if being sp2 and making one of his lone pairs in a p orbital and part of the pi system makes him aromatic, he'll do it. If it makes him anti-aromatic, he won't do it. So in this case then, one of these lone pairs possibly counts if he's sp2 hybridized. And in this case, that would be 2, 4, 6 pi electrons. So, and that's definitely an aromatic number. And so it turns out that, yeah, he's going to be aromatic. One of his lone pairs is in a p orbital. The other one's just in an sp2 hybrid. And so again, the key is the oxygen here is not involved in making a double bond in our structure. That's the first thing. And so unless, one of these lone pairs counts as pi electrons, otherwise he'd be sp3. So, but putting one of these in a plain old p orbital makes him sp2 instead. So, and counts one of the lone pairs as pi electrons, and 2, 4, 6 is indeed an aromatic number. Now, in the next one, we've got two different nitrogens that each have a lone pair. Now, in this one right here, that lone pair does not count. That nitrogen, it does not count as pi electrons, I should say. That nitrogen right there has a pi bond right there. There's its pi electrons. And again, you can't have two sets of pi electrons as part of the same parallel system of p orbitals. Even if they were both in p orbitals, it'd be two perpendicular p orbitals. So in this case, the lone pair is not counting as part of the pi electrons. But this lone pair might. He's not involved in making any pi bonds. So if he's going to have some pi electrons to be part of this conjugated system, it would have to be the lone pair. And if that's the case, it would be 2, 4, 6 pi electrons. And so he's like, yeah, let's do it. That makes me aromatic. And so indeed he is aromatic. So again, he was cyclic and conjugated, check. Any sp3s in the ring? Maybe not. In this case, it turns out not. So planar, smaller than 7 atoms, so he definitely could be planar. And then it turns out, as long as we count the lone pair on that nitrogen, and make him sp2, not sp3, then yep, 2, 4, 6, and he's aromatic. All right, this next one here. So our first example of something bigger than 7 atoms. And again, when you have more than 7 atoms in a ring, some can be planar and some cannot. This is one that you are typically expected to remember cannot. So it turns out if you take a look at the three-dimensional structure here, it looks like this, and it kinks. And because it is not planar, so you do have some conjugation going on here, but it's not going to be this nice system of overlapping p orbitals because they're not all parallel to each other. And so it turns out you do have some level of conjugation going on, but it actually turns out because they're not all parallel, it can't actually delocalize all the way around the ring. And so as a result, it cannot be planar. And so if you looked at this, you'd say cyclic and conjugated? Well, it looks like it is. Are there any sp3 atoms in the ring? No, they're all sp2. Is it planar? No. And so it turns out, since we've identified as not being planar, that this guy is non-aromatic. Now, sometimes you're not on the hook for such knowledge. Most of the time you would be, but some of you guys are not going to be on the hook for this. And so sometimes they'll ask the question a little bit different. And they'd say, if you look at this structure, assuming that it can be planar, what is it? Well, if you assumed that it could be planar, well, then we'd satisfy criteria 3 based on that assumption, and it would be cyclic and conjugated, no sp3s, planar, but it would have 2, 4, 6, 8 pi electrons, and at that point, that's a multiple of 4. And so if we assumed it could be planar, then it would actually end up being anti-aromatic instead. So again, in reality, it can't be planar, and it's non-aromatic. But if the question you got, because sometimes, again, with these bigger rings, sometimes they're going to be planar and sometimes not. So some professors just try to oversimplify things. And when they ask the question, they just say, assuming it can be planar. And just take that off the table so you don't have to know much. It's actually doing you a favor. Well, again, if we assumed it could be planar, then it's anti-aromatic. If we know that it can't be planar, then we'd have to identify it as non-aromatic. So hopefully you see the difference there. Let's look at some more examples. All right, our last 3 examples here, and these first 2 are not exactly what's on your study guide here. We'll modify them in a second, but if this is what we actually were determining here, well, then you'd have to identify this carbon up here as being sp3 hybridized. It's got 2 hydrogens. And this one also got 2 hydrogens, and it'd be sp3 hybridized. And because both of these would have an sp3 hybridized atom in the ring, they would fail rule number 2 and be non-aromatic. However, on your study guide, you'll notice that these are carbocations. So in being carbocations, it means they don't have 2 hydrogens, they only have 1. They only have 3 bonds total, not 4. And so being a carbocation with just 1 hydrogen, notice if we draw that 1 hydrogen in, we'll see that he's only got 3 electron domains, and therefore he's sp2 hybridized, not sp3. And being sp2 hybridized, he does have that third p orbital is being just completely unhybridized, but being a carbocation and having no electron density here, it's an empty p orbital, but it is still a p orbital, and it could be delocalized. Notice we could do a lot for drawing resonance structures, so involving that carbocation being in different locations. And so in this case, we'd say cyclic and conjugated, yes. Any sp3s in the ring? Nope, they're all sp2. So planar, yeah, he's smaller. He's 7 atoms or smaller, so definitely be planar. Then the question really comes down to the number of pi electrons. And so in this case, I'm going to just erase that hydrogen. It's still there. So both of these are in the same boat at this point. They both passed the first 3 rules. Cyclic and conjugated, no sp3s, planar. So the question is, though, is the number of pi electrons. So notice with a carbocation, it's an empty p orbital. There's no electrons there, so we don't get to count anything when we're counting towards pi electrons, but it still can be a conjugated system and have every, a cyclic ring of delocalized p orbitals there. So in this case, it'd be 2, 4 pi electrons, and 4 pi electrons, that's a multiple of 4, an even number of pairs, that's an anti-aromatic number, and there's nothing we can do to get out of it. It's just simply anti-aromatic. But in the next one here, we've actually got 2, 4, 6 pi electrons, and that is an aromatic number, and indeed he is aromatic. So life is good. So just wanted to show you that a carbocation is another way we can end up with an sp2 hybridized atom and not have any sp3s in the ring. All right, this last one is a more complicated example of what we call an annulene. So benzene itself is an annulene where you just have alternating single and double bonds all the way around in some sort of ring. And some of the annulines end up being aromatic versus nonaromatic versus antiaromatic, depending on the number of pi electrons and depending on if they could be planar. This is an example of one that actually can totally be planar. So when you look at this, then you say cyclic and conjugated, check. So it is cyclic, and it's alternating single and double all the way around, so it's conjugated. So any sp3s? Nope, every carbon in the ring is an sp2 hybridized atom. So planar, that's the rub. This is an example of an annulene that you probably should know can be planar. So if you look at the total number of atoms here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, commonly known planar annulene. All right, so then we got to say, well, how many pi electrons are there? Well, 2, 4, 6, 8, 10, 12, 14. And 14 is a 4n plus 2 number. It's not a multiple of 4. So 4n plus 2 is 7 pairs, an odd number of pairs. And this thing is indeed aromatic. So if you notice, I don't really have a steadfast rule for you to know when a larger ring, one that's 8 atoms or bigger, is going to be planar or not. However, I did show you an example of one you should know can't be planar, and now I've shown you one example of this one that you should know can be planar. So your 14 carbon annulene ring is indeed planar and is indeed aromatic.